How much time do we have? Would we like for the break? Hello. Hello.
Yeah, we can hear you, but I forgot when it started.
Sorry. It started, I believe, like 7 or 8, right?
Okay, then we had got 1 more minute.
Actually, it's even apparent from here. So partial derivatives are switchable. So yes. Sorry, I wasted a lot of time for nothing. Okay, let's erase this thing. We'll start within 1 minute. Hello. We can start, right? Is everyone here? Let's check.
Yeah.
Let's check. So Durjoy is here. Arafat, are you here?
Yes, I'm here.
Humayra bint Awal, are you here? Pooja Bajaj, Miss Pooja Bajaj, are you here? Hello. Prashanta Chakraborty, are you here?
Yeah, I'm here.
Zubaida Karim Juthi, are you here?
Yes, I'm here.
Okay. Okay, great. So the problem is like it's even apparent from this line that these last two terms cancel out, but I wasn't able to see. So the thing is, we expanded everything using chain rule, right? So we can actually recollect the chain rules like for these terms. So we have delta alpha x nu. Here also we have delta alpha x nu by delta x nu prime. So if you collect that two term, you can write as derivative with respect to delta delta x nu prime, right? Also, you can do the same thing for the other one as well. So now you notice that you have like same coordinate like delta x mu, but you are taking derivative with respect to two partial derivatives, one with respect to delta x mu prime and delta x nu prime. So prime coordinates like delta x mu prime and delta x nu prime, those are two different prime coordinates. So those are independent, and we know that partial derivative can be switched. So basically, by switching partial derivative, this term actually you can write alpha mu delta x mu prime of delta x mu by delta x mu by switching partial derivative, like the order of partial derivative. So then this term and that term cancel out, and we are left with only the other part. Oops. We are only left with the other part, that is equals to, let's also factor out the other things like delta x mu by delta x mu prime, like that. So delta x mu by delta x mu prime, if you factor out that and then also factor out delta x mu by delta x mu prime, then you're left with delta alpha mu by delta x nu minus delta alpha nu by delta x mu, right? So that is our beta nu prime mu prime. And we can see that this is what?
Beta nu mu.
It's beta nu mu. So we can see that with this definition, our beta nu prime is transforms like delta x nu by delta x nu prime, delta x mu by delta x mu prime, beta nu mu. So which is a second, which is the transformation rule for a second rank tensor, and that we have been expecting as well, right?
Yeah.
So the way we defined our derivative is then actually consistent with a tensorial like tensorial formalism. So which is a tensor basically. That's what we mean. So like the definition, remember, definition we did is dA is like this, right? So that's the definition for exterior derivative for one form. So we can actually let's write it down again. So d alpha we have defined as take the derivative of alpha component of alpha with respect to the coordinates and take this dx mu wedge dx mu, like that. So now as you can see, alpha mu, those are the components, those are just numbers, right? Like more like a scalar fields, right? Those are not a directional thing, the components only.
Yeah.
And also we know that for a scalar field, df is basically delta f by delta x nu dx nu. So we can collect this part to be like what? We can collect that part to be what?
D alpha mu.
D alpha mu, where D is the like the exterior derivative of a scalar field like thing. D alpha mu, then take wedge product with the rest. So this was the extension for one form, like how to take derivative of one form. We can, like, this is kind of a general thing, right? So we actually expand the definition for arbitrary p form to be like this. If you have a p form like beta, which is 1 over p factorial, then beta mu1 mu2 up to mu p dx mu1 wedge dx mu2 wedge up to dx mu p, right? This is your beta. then the exterior derivative, which is basically a tensor quantity, is defined as d beta equals to d of this scalar like part, that is 1 over p factorial. You can actually take that 1 over p factorial out of this derivative as well. Beta mu1 mu2 up to mu p. So this is one form. Then take wedge product with the rest. Dx mu1 with dx mu2 up to dx mu2. This is the general definition for an derivative of an arbitrary p form. And when you take derivative like d, that antisymmetric derivative, that gives you p plus 1 form. So I'm sorry, actually, today I wasn't probably in my best shape. So yeah, I wasted a lot of time. It should not take this much. Any questions so far?
I didn't get the motivation of the exterior derivative. How
So
do we define? Yeah.
Why wanted a derivative that is completely geometric, that doesn't depend on anything, any coordinate. It doesn't have any coordinate dependence. That's what we wanted.
By why specifically in that way? I mean, what is the physical interpretation of it?
The same as like p plus 1 form, like arbitrary p form has the same, the physical interpretation like that. So probably you want to be like a geometric interpretation that we have for slopes, right? Like for curve, you have a slope like that.
Actually, I want something, an interpretation that is consistent with that definition. I mean, we want a geometrical thing. There are other definitions which can be geometrical, but why in that way? Why did we define in that way? I mean, the p plus 1 form.
Okay. So why particularly antisymmetric way, right? That's what you mean, probably.
Not antisymmetric. At first, I want to know why p plus 1 form. Why the exterior derivative?
The result. That's all, because we already have for a scalar we had 0 forms, and we already have defined like df, which is like 1 form. So if you extend that thing, it continues, right?
Okay. Yeah.
So that's basically like extension of this thing. That beta to d beta is an extension of f to df.
So from here we can say that we need to define such that it is a wedge product or a direct product up to 1 form. So we get
yes. We wanted to be something like direct product of 1 form or something like that. Like,
yeah.
And if this thing is sure that d, which is derivative, that you can go in any way, that will give you the rate of change. So as you are not specifying the specific direction of what you are going, so it's kind of a vectorial quantity, right? So
yeah.
If you add a like mn tensor, then that finding the rate of change of that tensor will increase the tensorial index. So the way we want, or actually the way calculus works, it should always be like this for an arbitrary tensor. That's for sure. So because if you have a stress tensor, say stress tensor is a 3 by 3 matrix, right? which is a 0-2 tensor here.
Yeah.
It's a in 3 dimension. It's a 3x3 matrix. So now you could say that how much the component of that tensor. Okay, let's write, then it will be clear. So this is the matrix, say txx, txy, and so on. So now you could ask how much this component changes when you go in the x direction. How much does that change when you go in the y direction, like that. So only this component could have 3 possible derivative, possible independent derivative. That is x derivative. How much does that change when you go in x direction? How much does that go? How much does that change when you go in y? And how much does that changes when you go in z direction? So when you take derivative of txy part, that's already like giving you something that has 3 components. So in total you had 9 component. So taking derivative of everything, you'll get total object that has 27 component, right?
Yeah.
So that's for sure that it increases the number of indices in your tensorial value. So now even when you're trying to extend like the derivative of txy, say, so that probably you want it to be same way that d works, right? The gradient works. So already we know that gradient is a 0-1 tensor. So basically this thing. So dx mu, right? So for any arbitrary tensor, we actually want our derivative to be, for an arbitrary tensor of mn type, you want the derivative to be a tensor of type m n plus 1. That's already we are convinced.
Yeah.
Now the problem is, as we have seen that if we define directly, like as we defined our gradient the same way, the object doesn't become a tensor. That's the problem. We want it to be tensorial, because otherwise it won't be a geometric object. So that's why we wanted this antisymmetric way.
Okay, but we did define it using weight product. So how can we use it for general tensors?
Oh, we cannot. We cannot use this definition for an arbitrary tensor, obviously.
So
This
we
definition works
extend
for
it.
only p forms. It's a derivative for p forms only.
Oh, exterior derivative only is for p forms.
Yes.
Okay.
So look, you notice that I have been looking into some books and saying that, okay, no, this book doesn't help much. So there is a reason, actually, because on manifold, actually manifold means space, the place we are working on, that might have some properties that, like, metric tensor could be defined or not. Right?
Yeah.
So there is a structure, even without the metric tensor, that could be defined. That's called connection. But here, the space we are working on, we haven't defined any connection on it. But the derivation that in every book it does using the connection. So that's why I cannot like use that directly. So okay, so that connection is actually it tells you how to take derivative of a vector or something like vectorial object. So to take derivative for anything other than p form, you need to have defined a specific structure to take derivative on that space. Otherwise, you cannot take derivative. But this derivative is all defined everywhere.
Okay.
You see what I'm saying? you need an extra structure on the space to take derivative, but like arbitrary derivative. But for this kind of derivative, we do not need anything else. That's the advantage of exterior derivative.
Don't we need that kind of derivative?
What kind of derivative?
I mean, that kind of derivative which need connection defined.
Okay. So connection, the definition of connection is required when you take derivative of any vector-like quantities, or any quantity that is other than P form, like completely antisymmetric. We'll see that we are going to study in a lot detail, because that's all about GR.
Okay.
But to do exterior calculus, you need not that connection defined. If metric is defined, the connection is already defined. That's not a problem. But we are not talking like when we are taking derivative, like exterior derivative, the metric tensor may not be defined, right? We haven't assumed that.
Yeah. This definition is also works also for P vectors.
No. It's for P form and only P form.
Okay.
You cannot apply this thing on P vectors or anything. To take derivative of P vector, you need connection. When you want to take derivative of any kind of vectorial quantity, like anything other than P form, you need connection defined.
Okay.
Okay. It's a lot of discussion. So let's see who we're able to follow so far. Durjoy, are you able to follow?
Yeah, I'm following.
Okay. So Arafat.
I joined a little late, so
Sorry.
I joined a little bit late, so I didn't find previous calculations. But don't worry, I can follow.
Miss Bajaj, are you here? Hello.
Yeah, I'm here.
So,
Yeah, I'm kind of able to follow.
okay, so did you get that last part where I was stuck?
Yeah, I get that.
So that's basically here, like I just missed this thing.
Yeah.
Important, but I wasn't able to see today.
Yeah, no problem. Yeah. Like it happens, it can happen to everyone. Yeah, it's okay.
Okay. Ankon Dash, are you here?
Yes, sir, I'm here.
Are you able to follow?
Yes, sir, somewhat, sir.
Don't call me sir. Okay. Then Zubaida and Humaira.
Yes, I'm trying to follow.
Okay. So at least we are on the same page that exterior derivative, it applies on P forms only, number one. And when you apply it, it gives you a P+1 form, and that's it. Like we still do not know how to take derivative of a vector field. But we do not bother about that at this point, because we know now at least how to take derivative of electromagnetic field, because electromagnetic field falls in this category because it's a two form. So when you take derivative of electromagnetic field, it gives you three form. Okay. So now we have a almost general definition, but mathematician probably would want the definition to be somewhat more abstract. So usually a mathematician defines an exterior derivative to be like this, with these two definitions. One is for one form, so for zero form, for scalars, when you take df, you get one form, which is the gradient, like defined like delta f by delta x mu dx mu. Or basically the definition of df, we already seen how it's defined. Now, in addition to this, for arbitrary p and q form, it's defined like this: d on alpha, which is a p form, wedge beta, which is the q form. Then it's defined as d alpha wedge beta, then plus minus 1 whole to the power p alpha wedge d beta. This is the definition of a mathematician. It's abstract, but it's the same definition as we are encountering here. But okay. So actually, he would say two things to define fully. Another is d on anything, any arbitrary form is always 0. Usually double d is written as d2. So d2 of anything is always 0. It doesn't matter what alpha is. Or basically a mathematician would want to write like d2 equals to 0. So with these two statements, you can actually reconstruct all the things we have actually saying, like the way we defined our d phi or d alpha, you can actually reconstruct that. So it's just a bookkeeping, that's what I'm saying, but we are not mathematicians, so we are not going to use that explicitly. Sometime it will be helpful to remember this thing. So this property, actually d2 equals to 0, this we should actually explore a little bit, right? So let's see. For alpha, which is a p form, we can write as 1 over p factorial alpha mu1 mu2 up to mu p dx mu1 wedge dx mu2 wedge dx mu p, like that. Then d alpha is 1 over p factorial delta alpha mu1 mu2 up to mu p by delta x say nu dx nu wedge dx mu1 wedge dx mu2 up to wedge dx mu p. That we can do, right? That's the definition of d alpha. Then if you take derivative again, d2 alpha would be 1 over p factorial. Then you have to take derivative of this part again, which is delta alpha mu1 mu2 up to mu p by delta x say lambda delta x nu. Then you have dx lambda wedge dx nu wedge dx mu1 wedge up to dx mu p, right? This would be your d2 alpha, right?
Yeah.
So now if you switch these two things, dx lambda wedge dx nu, you get a minus sign, right? So it's an antisymmetric thing. So the whole object is antisymmetric with respect to the indices lambda and nu. But here you can see that you have partial derivative with respect to x lambda and x nu, which is basically symmetric. When you switch those two indices, nothing happens, right? So you are multiplying a symmetric object with an antisymmetric object. What you should get? Do I need to show it explicitly, or you can see it, it's 0? Should I show
I
it?
didn't get that.
Okay. Yes, it's okay. So now this object is symmetric with respect to the change of the indices. That means so here you are taking derivative with respect to the x nu first, then you are taking derivative with respect to the x lambda. But it's a partial derivative, and we know from the properties of partial derivative is that you can actually switch those two things.
Yeah.
So let's call it beta. Let's call it this second derivative beta with p plus 2 indices, obviously. So beta should have like lambda nu, then mu1 up to mu p. Mu1 up to mu1, mu2 up to mu p, like that. And here we have seen this is just equal to beta nu lambda, because we are taking lambda derivative first, then we are taking nu derivative. Nu lambda, then mu1, mu2 up to mu p. So it's symmetric with respect to the first two indices, but this whole thing is a p plus 2 form, which is completely antisymmetric with respect to any indices, right?
Yeah.
So because of this being p form, so we already know that beta lambda mu mu1 mu2 up to mu p, if you switch any two adjacent indices, you should get a minus sign, right? Which is minus beta mu lambda mu1 mu2 up to mu p, because it's a p form. And because it's the partial derivative switch, this is also equals to the beta nu lambda mu1 mu2 up to mu p. So you see that
has
this
to be
object which is negative of itself. So what is the quantity whose negative is equal to itself?
0.
0. So beta must be 0.
Yeah, got it.
Is that clear to everyone? So if you apply exterior derivative twice, it becomes 0. Because of the partial derivative can be switched. So okay, so we are done with exterior derivative. Now the fun part, the calculus, like the integrals. So there is a definition. Start with the definition and we'll see how it gives you the correct thing. So definition of integrals here, if you have a p form alpha is a p form, so integration on alpha, like let's definition this operation, like this integral sign is defined as a map between alpha, which is actually omega p, which is a p form, like alpha is a p form, so let's write down this, to the real number. So if you just apply integration on any form, it gives you a number, purely number. And what's this is the formal thing, like how integral operates. And the definition is if you have a p form alpha, then integral of alpha is defined as, actually that's not right. Okay, so this is some lambda 1. I'm going to tell you what's lambda and lambda 2 and lambda up to n. Actually p minus 1. minus 1 lambda p. Definition is piercing of alpha with delta p by delta lambda 1, which delta p by delta lambda 2 wedge up to delta p. P is the point, so delta p by delta lambda something is basically a vector. So you are taking in a p number of vector to produce a like p vector. So you're taking piercing, and then it's a number. This piercing gives you a number, and then you just perform a multiple integration over ordinary multiple integration over this value. So what it means is, say you have a two form, alpha is a two form, say particular case. So now this thing can be integrated on a two-dimensional region only, number one. So say this region, this two-dimensional carpet on which you can integrate alpha. So then what you have to do, you have to parameterize your carpet like this. And then you have to pick which one is your first coordinate, which one is your second coordinate. And you have to define that two thing, and then you pierce two thing, and then when you do this piercing, like delta p over delta lambda 1 with delta p over delta lambda 2, this thing will give you the area covered by two adjacent grids, right? Like this thing, infinitesimally separated two grids. That will give you the area. Then you are multiplying by the magnitude of each of those, so which is d lambda. So, and then you are integrating. That means you are actually adding all those possible pieces. So that will give you the total area. So that's how integral of alpha is defined. Confusing?
Can you please repeat the example?
Okay. Okay. Consider you have an electromagnetic field F. F is an electromagnetic field. So say magnetic part like BZ, which direction does it orient? Or what's the like the basis for that BZ part? Dx wedge dy, is that correct?
I'm not sure actually. Is it? Did you learn electric field with wedge products?
I think it's correct.
Okay. Yes, we learned that. We saw a general electromagnetic field, like when you have all the possible components of electric and magnetic field, then we had like 6 things, remember?
Oh yeah. This.
Okay. So what it means is, say my whiteboard is your two-dimensional surface, which is on XY plane, and the Z direction is pointing outward. Now you have your electromagnetic fields as tubes, right? These tubes that are coming out of the plane, these represent your magnetic field BZ, right?
Yeah.
There are many more. So now if you say you want to compute the integral, which in this case would mean the flux integral actually. So if you want to integrate F, that would mean actually you want to find how much the magnetic field time area you have, which is basically the flux of magnetic field. So to do that, actually, I am drawing this grid as like kind of to represent things, but in principle, when you have a magnetic field, you do not have those grids, right? You cannot see those grids. That's a flat space. So first to integrate that thing, you need to set up a coordinate. In other way, you could say you want to set up a parameterization.
Yeah.
So on this plane, you set up a parameterization, say like your usual Cartesian grid. That's your parameterization. So this way, the coordinate you name it as lambda1. In this way, the coordinate you name as lambda2, which are basically x and y. I'm just trying to teach it generally. That's why I'm calling it differently. So now if you take an infinitesimal vector that is along with this lambda1, which has a magnitude delta lambda 1, then the vector would be like, say, v1. Let's call it v1, or let's call it u. Let's call it u would be like delta lambda 1 times the direction, that is delta p by delta lambda 1, right?
Yeah.
That is your infinitesimal vector. The same thing is true for a direction which is aligned in this way. Let's call this thing as a v. V would be your delta lambda 2 delta p tilde by delta lambda 2, right? Magnitude times direction.
Yeah.
So now the area covered by UV, like the two vector constructed out of those two vector should be u wedge v, right?
Yeah.
Which is delta p tilde by delta lambda 1 wedge delta p tilde by delta lambda 2 times delta lambda 1 times delta lambda 2, right?
Yeah.
So if you pierce that thing with F, what you get is delta p. Okay, you get like F times that. Now, as we want to show explicitly, now at this step, actually, we substitute that, as I said, like lambda 1 are x and lambda 2 are y. Let's substitute those explicitly. Then you get piercing of bz dx wedge dy, right? Pierced with what? Delta p by delta x. What is that? Just ex, right?
Yeah.
Wedge, then delta p by delta y, which is ey. Then you have delta x, delta y, right?
Yeah.
Which would be your bz. It comes out of the piercing process. Then delta x, delta y, it comes out of the piercing process. Those are numbers, and you are left with this part. So what is the piercing of those between those two? We have learned it.
Kronecker delta.
Yes, Kronecker delta what?
XY, XY.
Yes, Kronecker delta. You have bx delta x delta y. Kronecker delta x xy xy. And what's the value of Kronecker delta xy xy?
1.
It's just 1, so we need not to write that. So that much flux is represented by this piercing, that is bx delta x delta y. So what does that mean? Because that means that if you have an infinitesimal piece that that is length delta x and width delta y, that area includes a flux bx delta x delta y, which is correct, right?
Yeah.
Now, if we add all those possible pieces, that will give you the whole flux, right?
Yeah.
And that is basically like your double integrate integrate this thing.
Yeah, got it.
So your that integral that you get, that basically measures that, in principle it measures the area actually, or flux, or you could say volume, or total, like integral of total density, like that, depending on what you are integrating.
Yeah.
So it'll be much more clear when you do some example. This is just the definition. We need to get comfortable with this definition. So this actually generalizes the idea of our integration.
Okay.
Okay, so we'll just see one last theorem and we'll just do problem with that, then it will be clear. So do you guys have any that book of Shom's outline, like vector calculus book? Like I need some problem from you so that I can perform here some easy problems. Please find the book and like put it near to you.
Okay, I have the book.
That. Okay. Okay. So the theorem I'm going to show that when you change the coordinate for an integration, that's basically gives you like multiplying by the Jacobian. That's what it gives you. So the definition of integration of alpha is basically integrations over this thing. So if my parameterizations are like the coordinate parameterization, then this thing. I could write it in a more general way though, but I need not to. So this is the definition. Up to dxp, right?
Yeah.
Okay. Now we have already seen the example where like how you change the representation of alpha. Like we have already seen one theorem, right? So how dx wedge, dy wedge, this thing changes. You remember?
Transformation of
Okay, let's prove it here again. Let's prove it here. Okay, so we have this. Now, if we change the coordinate into a new one, which is say y1, y2 up to yn.
Okay.
Then in terms of those transformed coordinate, we can write like the transform basis vector is like delta p tilde over delta x1 becomes delta p tilde over delta x1 becomes what? Delta y delta y I, which I sums from 1 up to p, by delta delta x1 delta p tilde by delta yi, right?
Yeah.
And we have to do the same thing for a p number of things. So let's write it as pi. That will be, I think, better. Like, let's generalize this thing. Oh, sorry, I1. Then write like this. I2. I2 are indices, actually, different indices. We need many more. That's why we are actually writing that way. P by delta x p delta p tilde by delta delta y I p, like that. Then you have like dx1 up dx2 up to dxp, like that. So I want to take these numbers like delta xi by delta x1. I want to take those out of this piercing process. So I get delta x delta yi 1 by delta x1 delta y I2 by delta x2 and up to delta y IP by delta xp, like that. Then I have like alpha pairs with delta p tilde by delta y I1 with delta p tilde by delta y I2 with up to delta p tilde by delta yip, like that. Then I have dx1 dx2 up to dxp. So remember, this wedge product, it's a completely antisymmetric object, right? It's a completely antisymmetric object.
Yeah.
Due to its complete antisymmetry, we can use E sign, like E, to represent that, right? So if we introduce E to write like this, how can we write this thing? It has p number of objects wedge product of p number of objects. So we can write 1 over p factorial, then Kronecker delta say mu1 mu2 up to mu p I1 I2 up to IP. I can do that. Then like I can write delta p over delta x delta y mu1 up to width up to delta p over delta y mu p, like that. And then I have like dx1 up to dxp. Is that correct?
Yeah.
Okay. So what is the relation between this Kronecker delta and E? What is the relation between Kronecker delta and E?
It's multiplication of 2e.
It's a multiplication of 2e, just multiplication, right? So I can erase that and I can actually write E mu1, mu2 up to mu p, and then E I1, I2 up to IP. Is that correct?
Yeah.
So now if I take this thing here, what do I get? Now definition is just double sign. EI1 up to IP delta Y I1 by delta X1 up to delta Y IP by delta XP. Then let's write the other part like 1 over p factorial, because those are numbers, so I don't care much. Mu1 up to mu p alpha waste with delta p tilde by delta y mu1 up to, like we are keeping those both product, then delta p by delta y mu p, like that. Then dx1 up to dxp. So do you recognize this object? Do you recognize this object?
Yeah.
It has the relation with the Jacobian,
Yeah.
right? What's that?
Uh,
So those indices on X, that becomes the lower indices with E, E1 up to EP, like that.
then the Jacobian determinant.
Then Jacobian determinant, which is just J. J of what? J of Y to X, right? Like
Yeah.
when you go from X to Y coordinate, that's the Jacobian. Then you have 1 over p factorial then you have your E mu1 up to mu p. Then you have like this thing, alpha, blah blah blah. You know what I mean, right? It's just the upper one.
Yeah.
Okay. Okay. So now, what is E1 up to EP? When all those things are in order, because that's how we define the integrations already. You have to choose a particular orientation. So what's the value of E?
No, it's 1.
It's just 1, because those are, every indices are on order, right?
Yeah.
So okay, that becomes this. So it's 1. So it gets you this J Y by X 1 over p factorial E mu1 up to mu p. But here I have like delta X Y mu1. I do not want that. I want delta Y1 with delta Y2 and so on. What should I do?
I didn't get your question. Can you repeat it?
I'm saying I do not want my delta p by delta y1.
You mean you don't want
I
Can
do not want one. I want y just one. Here, those are arbitrary indices. I do not want arbitrariness. I want oriented indices.
You can use similar with Kronecker delta technique.
Not Kronecker delta. I have to use epsilon.
Okay.
So you remember this thing? This object can be written as p factorial e mu1, mu2 up to mu p, then delta p tilde by delta y1 wedge up to delta p tilde by delta y p. Remember?
Yeah.
Yes, right.
Okay. So these two things cancel out. And this thing, what do you get? You get another p factorial term, right?
Yeah.
And you have your alpha delta p by delta y1 wedge delta p by delta yp and dx1 wedge dxp. So yes, this is my integral in when I consider that integrand in a new coordinate system. As you can see, we have our Jacobian over there.
Yeah. So
Okay.
next year, algebra and calculus.
Satisfied yet? You should
Sorry?
not at this point.
I didn't hear that. Sorry.
You should not be satisfied at this point because usual way like this is a one important result, because we are going to, in many cases we want our integrand to change but not the differential, but sometimes we want our differentials to be changed as well when we change the coordinate.
Yeah.
So what should we expect when we change the differentials as well? We change the piercing process only, not the differential.
Another Jacobian determinant.
Yes, Jacobian and what? So the only thing that will be changed, there won't be any p factorial, and d, instead of dy1 we should have just y1, dx1 we should have dy1. That's we haven't got here, right? But this one important result, because we are going to use that in many cases. So how should we proceed if we want that result as well? There's just when you perform everything in a different coordinate, like do not change the coordinate at all, like start with a whole different coordinate.
We can use the chain rule in the dx1, dx2 terms.
We can use, yes, we can use the chain rule when we started at the beginning, right? Like over there. Where? Yeah, like when we started, like at the very beginning when we started. Okay, we can do that as well. So let's do that. So remember this part. So this is one result of one integration of alpha that comes from the definition. So when you do this, remember this p factorial, because otherwise, like, it'll be off. Okay. Now I want my coordinate to be completely changed, not just the integrand, like the coordinate of integrand. Okay. Let's start with the definition of the integral itself, which is delta p tilde by delta y1 in y coordinate. Oh, by the way, did you write the correct Jacobian? Delta x, yes, it's the correct one. It's the correct one. Okay. In y coordinate, actually we should start with x coordinate again. I think it works. Okay. So this is basically delta p tilde by delta y1 dy1 with up to delta p tilde by delta yp dyp, like that. If I expand the dy1, it will give me I am expanding dy1, which is going by chain rule is going to be what? Delta y1 by
Which is the x.
delta x, say mu1, right?
Yeah.
Dx mu,
Dx mu.
like that. And similar thing repeats. And then we have like delta p tilde by delta y1, sorry, delta yp, delta yp by delta x mu p, then dx mu p. Right? Now we can take those dx mu, because I wanted my dx here. I'm just going from x coordinate to y coordinate. So gives you delta p tilde by delta y1, delta y1 by delta x mu1, wedge up to delta p tilde by delta y p delta yp by delta x mu p pierced, and then dx1 up to dx mu p, right?
Yeah.
Okay. Okay. Then okay. First, let's handle this part. Here we have mu1. So we have arbitrary indices. I do not like that. I want here to be 1, 2, 3 up to p. So what can I do about that? Remember, when you switch those mu1 indices, you get a minus sign, because here, like, those are inside of those wedge product. So I can use that thing here. Or actually, let's pull up Kronecker delta out of that. That will be helpful, like easier to understand. Okay. When I switch these two indices, like mu1 and mu p, that gives me mu1 and mu2, that gives me a minus sign. So I can add a Kronecker delta with lower indices like mu1 up to mu p, and I have p summed over. So I should have 1 over p summed over gives you 1 over p factorial, right? And then I have like taken those mu1, mu2 in consideration. So the next thing I need, the algebra is getting weird. Can we make it simpler? So the first term is just 1. The second term is everything is 2, and like that. Summed over mu1, and then I think for x I'm actually substituting like 1, 2, 3. So 1, 2 up to p. Yes, that's correct. So I have like piercing delta p tilde by delta y1, delta y1 by delta x1, and so on. Okay, do you get that what I did here? So here actually I'm planning to take that, using that anti-symmetry. I just want my x to be like in sequence, like 1, 2, 3, like that. So to do that, I have introduced this Kronecker delta. So those mu indices are summed. So it appears like p factorial times more, right? Or p factorial times less. Crap. Okay, let's remember the identity, because probably I screwed up it here. So for beta, if it has like mu1 up to mu p, those are antisymmetric indices, then I have like Kronecker delta mu1 up to mu p, mu1 up to mu p, and then beta mu1 up to mu p. And where is the factor? Here or here? Like, what's the factor here? We learned this earlier.
I think it's left hand side. I mean, p factorial into become mu 1 mu 2.
This one?
Yeah.
Okay. Okay. Now match it over there. Which one is correct? So doesn't seem right. Or no. Yes. This one is correct. Yeah, this one is correct. Yes. So I have 1 over p factorial over there, and I think then the way I substituted is correct, pretty much correct, right? I think it's correct. Okay, so I can take that, take everything out of those, like every factor out of those wedge product part, and I'll be done by doing that. Okay, so I have this thing. No, I have like Kronecker delta 1 over p factorial, Kronecker delta mu 1 up to mu p, 1, 1, 2, 3 up to p, then 1 over p factorial. Then here is another thing. I need to switch that thing as well. Actually, I should have done it earlier. Or I can do this thing as well here. Okay. Then I have like delta p tilde by delta y1, which is a vector, and its coefficient is delta y1 by delta x1, and so on, right?
Yeah.
So what I can do, I can actually take these numbers out of this wedge product and do the other thing, like put those other thing in just single, like sequential wedge products, right? So that's what we want to do here. So delta y1 by delta x1, delta y2 by delta x2, and so on. Delta yp by delta xp. Then I have like delta p tilde by delta y1, wedge delta p tilde by delta y2, and so on. Delta p tilde by delta yp. Is it yp or xp? Oh, yp. Yes, yp. But I want okay. X mu 1 x mu p. But I want everything in terms of x only. I do not want my y. I'm trying to change everything into x coordinate. Let me think about it. Actually, it's not that complicated. Actually, I do not know what I'm doing today. This part should be like the simpler one. I don't know why simple algebras are like taking too much time for me today. Okay, okay. So I did the first thing. I expanded dx1, dy1, and expanded. I should have expanded the other one as well. If I expanded that correctly, then there shouldn't be a problem actually. Substitute that. Actually, I could have simplified over there. So sorry, let's erase all of this stuff and just proceed from here. So all I want to do is to introduce the Jacobian first, like the like all possible derivative, like delta x mu by delta x, like mu I or delta x mu by delta x nu. This kind of derivative I want to introduce. That's my goal basically. So every time I'm trying to do that and I'm getting stuck. Okay, first, then here I have like sequenced index 1, 2, 3 up to p. I do not want that. First, I want this thing, delta p tilde by delta y mu1 d d y mu1, like that. So what's the relation between these two things? That's I need to know first. Okay. So what's the relation between these two? Like here I have like sequenced one, and here I have an arbitrary one. So as I have an arbitrary one, I need a summation over all those mu indices, right?
Yeah.
Problem is it's not consistent with this notation. So that's another thing actually I'm confused about, like struggling today. So these indices, like even if those are repeated, those are not summed over. Even those are repeated index, those are not summed over. So we also know what does that mean though. What's happening to the simple thing I'm struggling with? Like these are like common thing, like you just showing the typical class. It's not that hard, but what I'm doing, even wasting a lot of time. Arafat, any idea? Hello? Last thing was easier, like also, did I make a mistake over there? Is this relation correct? I had delta p by delta y mu1, and I wanted to convert it into 1, 2, 3, like that. Is there should be a p factorial or not? Hello? Is anyone here or everyone left today? Sorry, I'm struggling today. I do not know. Okay, so is this result correct even? Like, that's what I'm thinking. Like, delta p tilde by delta y1. Actually, I had like delta, like as you can see over here, I had delta p tilde by delta mu1, which mu2 and up to like that. So the question I'm asking, what's the relation? So when I have like dx1, dx mu1 with dx mu2 like that, up to dx mu p, it is E mu1, mu2 up to mu p that handles the sequence of that. Then is it dx1 with dx2 with dxp? Because there are no sum over there, like there are no sum among those indices. So there shouldn't be a p factorial over there. Hello? Because when I try to use that in anywhere else, it'll give me like, it seems it'll give me a p factorial extra. So please look into the result. Which one is correct? Like, is this result correct? Or there should be a p factorial somewhere? Is this result correct?
I think so, because there is no summation here.
Yeah, there are no summation here. So
That is just dealing with the sign. I mean,
yes, we are dealing the signs. There shouldn't be a p factorial over here, right?
yeah.
So that 1 over p factorial should be over there, right? And if so, then we have again like sum over mu1, mu2. That will give me an extra p factorial, which will cancel out. So there, I think there shouldn't be any p factorial over there. That's the result only.
Yeah.
I think then actually I'm done. Then actually I'm done. So we just start with the integral of that alpha. Actually, I can use this result now. Yes. So then I start with like this. Integral of alpha is again in terms of the new code, like other coordinate, in y coordinate. It's just piercing of alpha by definition. Delta y p tilde by delta y1, which up to delta p tilde by delta yp, then dy1, dy2 up to dyp, right? This is by definition. So then I can equate the integrand like this, or those integrands are same. So I equate the differentials like dx1, dx2 up to dxp. Here Jacobian y over x equals to dy1, dy2 up to dyp. Then it's correct, right? Yes, 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 yes. This is the correct answer. Yes. Differential should be related by a simple Jacobian, nothing else. Okay. Lot of wasting time, but actually, so what I have proved here. Let's go back again and just check. So we had a definition of alpha. First, we had a definition of alpha. and we just use that in Cartesian in x coordinates. So we had two kind of coordinate, x and y. So in both coordinate, as integral of alpha, it's a coordinate independent thing. So integral alpha, it should be in two coordinate, can be written either in x or either in y. So all I have to check that what is the relation between the differential that we have been looking for, like what happens when we change the coordinate, and we have to change the differential. Like remember, in Cartesian coordinate, we usually, when we did volume integral of some f of x by z, in Cartesian coordinate we have like dx, dy, dz. But when we go into the polar coordinate, the same thing becomes, you do not change this f, just change the variables. Like that f remains same, but in terms of new coordinates. But instead of dx, dy, dz, we have, there is actually, what do we have? R square sine theta dr d theta d phi. So instead of just having dr d theta d phi, we have like a factor r square sine theta multiplied over there, which is basically the Jacobian of the transformation. So that's, I wanted to show actually that how Jacobian are connected. So expand the same result in one coordinate and also expand the same result in other coordinate. In what one coordinate you change into other, like make a change of variable into other such that the integrand matches. So here we have the integrand matches, like here we have piercing of alpha, like here basically we expanded, like written everything in terms of x coordinate, we expanded in terms of y. So here we have like alpha pierced with this object, and on the other way we have written directly in terms of y coordinate, and we match the integrals, and the left, like the differential, here we have just dy, dy1, dy2 up to dyp. In other we have dx1, dx2 up to dxp times the Jacobian. So that's the result I have been looking for. And I made a mistake over there, and I was trying to reconstruct that p factorial, but I shouldn't be able to, because that's already mistake, that shouldn't be here. Okay. So now these are simple results. Like usually I do not struggle that much like these topics. Okay, I think these are the formal theorem that we have learned. Now let's do some illustrative problem that will actually show us. So do you have the Shom's outline book for vector calculus? Let's see all the result that will come into one place. Just give me some problems. I have 1 hour left, so let's not waste more time. So give me some problem regarding integration of, like line integral problem, integration of a vector over a curve. Give me that kind of problem first. Please do it first. Do it first. I'm sorry, today, like it's a disaster. Today's class was a disaster. I made mistake in many places. Hello?
You want line integrals?
Yes.
Okay.
Usually they give you a vector field or a work, like they tell you the force field, and they want you to evaluate the work in Cartesian coordinate.
Okay, here's one. The force field has an expression of minus 3x squared.
Minus 3x squared, exact,
plus 5xy.
plus 5xy,
Y hat.
y hat.
And the curve is y is equal to twice x squared.
There are no z component?
No.
Okay, and the curve is?
Y is equal to twice x squared.
Y equals to twice x squared. This. Yeah. And the limit?
0.00 to 0.1.
Value of what? X, value of X?
X is 0, and 0 to 1 and 0 to 2. The value of X is 0 to 1.
0 to 1.
And value of Y is 0 to 2.
Yeah, that you do not need to provide. That's enough. Okay, so the question says you have a vector field and you have a curve, like these are the vector values. So they tell you how much you produce a work done from going from this point to that point. So if we want to do this same problem in terms of exterior calculus, first the integration on exterior calculus, it actually happens over a differential form, not a vector. So we want to convert this force field into a corresponding one form field, that is F lower bar. And can someone tell me what that thing would be? Hello, what's the metric tensor in Cartesian coordinate?
Dx.
So the metric tensor, because to do that we need a metric tensor, right? So ds square would be
X times dy.
x times dx,
Yeah.
plus dy times dy.
Yeah.
So they are considering only 2 dimensions, so I'm happy also with the 2 dimension. That's fine. So now if you want to find F lower bar, that would be what? You have to provide ds square with one slot empty and one slot supplied by F vector, right? Which would be, it's just diagonal and 1 1, so it should be simple. So basically you do the algebra and that the result will be minus 3x squared dx plus 5xy dy, that you will get because it's Cartesian coordinate. The component of one form and component of vectors are same basically. Now you want to integrate this thing over the curve. Curve is your region, basically defined manifold on which you are integrating on. So integration of F would be, by definition, integration piercing of F with how many vectors you need, like how many parameterization you need for one curve?
1.
Just one parameterization. So, and what's the convenient parameterization for this curve? Like
I think arc length.
This curve, like given curve, y equals to 2x squared. So it's already given you the parameter. So you could consider, like they haven't given you parameter, but you could actually choose your x to be your parameter as well. So the parameter in the parametric form, consider like the lambda is your parameter, then y equals to 2 lambda square. That's one equation, and another is x equals to lambda. That is the parameterization of the curve piece, right?
Yeah.
So the thing you want is delta p tilde by delta lambda, right? Then d lambda.
Yeah.
Okay. So now using the parameter lambda equals to basically x, right?
Yeah.
So you actually need not bother about that much. So this is this. That gives you F integration F pierced with Ex, right? Dx. Oh, now you also need to set the limit for lambda. What's the limit for lambda?
It's 0 to 1.
It's 0 to 1. Yes, the same limit for x. So what's the piercing of f and ex?
It's fx.
Just remove that part, right? So minus
Yeah.
3x square. So 0 up to 1 minus 3x square dx. And what do you get? You get minus 3 x cubed divided by 3, right? Or is that correct?
Yeah.
So which is basically negative 1. I think that's the correct answer. So that's how you do line integral using exterior calculus. So can you give me a surface integration?
Yeah, but dear answer is 7.
7?
Yeah.
Did I make a mistake in parameterizing things? Yeah. Why? Delta p tilde by delta lambda equals to, yes, I made a mistake. Today, as I cannot focus most time. Okay, so I have to use the chain rule to actually find the tangent vector to this thing. So delta p tilde by delta x by delta lambda, but I have other part here like delta p tilde by delta y by delta lambda. That's I didn't do. So okay, what do I get? Actually, I evaluated that thing wrongly. Delta p tilde by delta x is ex, and then delta x by delta lambda is just 1. Then delta p by delta is ey times delta y by delta lambda. How much is that?
4 lambda.
4 lambda. Okay, now that I substitute. So his basic definition is delta p tilde by delta lambda d lambda. Then substitute everything else. So it gives you f pierced with delta p by delta lambda is ex plus ey 4 lambda ey. 4 lambda ey, this thing, d lambda. Now you can actually switch to x coordinate, and for that we get 0 up to 1 f ex plus 4x ey dx. That's you can do. Then if you pierce that using the definition of f, what's that? So
Minus 3x squared.
minus 3x squared
Plus 20
x
x
squared
squared y.
y. Dx, right? You can also change your y to be twice
X
that
squared.
one, right? Yes. So negative 3x squared plus 20 x squared times twice x squared dx. Now integrate, it will give you minus 3 x cubed by 3 plus 40 then times 5, right?
Y times
not times. This, right?
Yeah.
So it's minus x cubed plus, what's the ratio? 8, right?
Yeah.
And the limit is 0 to 1. So at 0 it's 0, but when you substitute 1, you get
7.
minus 1 plus 8, which is 7. Yes, yes, the answer should be 7. Yes. Sorry. I'm not on my best shape, as I'm saying. Really, I'm just screwing up this line integrals today. Okay, give me a surface integration. So thing is, you parameterize, you find the tangent vectors, and you take the wedge product, and that's, you do not worry about the coordinates. Whatever the coordinate you are choosing, it's fine. Okay. Give me another. I'll just,
Surface integral.
yes, a simple surface integral, not a complicated one. Because
Okay.
I'm
It's on a plane.
Mhm.
The field has a expression.
Give me 3 dimension. Give me in 3 dimension.
Yeah, it's in 3 dimension.
Mhm.
If it
Field is
is equal to 18z exact.
what?
18z exact.
18z exact
Minus 12
minus 12
y hat.
minus 12 y hat minus 12 y hat
Plus 3y
plus 3y.
z hat.
Okay, and the space, like the
The
region,
equation of plane is twice x plus 3y plus 6z.
say it slowly.
Twice x plus
2x plus
3y
3y
plus 6z
plus 6z
is equal to 12,
equals to 12.
which is
And what,
located in the first octant of our coordinate system.
so first octant, so that means it's not the end of the story. Okay, so it's basically they are talking about like the region intersect with when x to infinity and intersect with y to infinity and intersect with z to infinity, like that. So it's a set of bunch of things, actually. Set of the all possible point that lies in this plane, but you have to take intersection with
The axis.
Okay, now we have a surface integration. So we'll take care of about the region later. First, take care about f itself. So the formalism you have developed, it works on p form, not vector. So how do you change this to be a some form?
Flat.
So we need to perform a flat operation on f, right? And it's a Cartesian coordinate. What will you get? Someone else.
Will be same. Okay.
Yeah, the metric answer will be same. Arafat, can you tell me what will it be?
It will be 18z
18z
dx
dx
minus 12 dy
dy
plus 3y dz.
3y dz. Now, if I integrate over alpha, that's alpha is a one form, right? Alpha is a one form, and if I integrate over that alpha, what should I get? Like, what kind of integration is that? Okay, someone else. But Miss Bajaj, if I integrate over alpha, which is a one form now, what kind of integration would it be? Hello? We just did one. Humaira? Hello? Just let me know you are here. Durjoy?
Yeah, it should be a line integral. An integral over a one
Yes,
form.
if you integrate over one form, it will be a line integral. So that's of no use. We want it to be an integration over a region. So a two-dimensional thing. So we want to convert in 3 dimension a line integral, like the integrand of a line integral to an integrand of a surface integral. What kind of operation do I need to do? Arafat, any idea?
We can take the Hodge dual.
Yes, we have to take the Hodge dual to find the corresponding flux density version, right? So beta would be a two form, which is defined by star alpha, which is basically star flat of F, and that's we have already learned earlier. If you take a star on this whole thing, what should you get in 3 dimension? Z, then it's x. So if you take star dx, what's that?
It's dy wedge dz.
Dy wedge dz minus 12. Then you take star dy. What's that?
Dz wedge dx.
Z wedge dx. Then
Plus 3y dx wedge dy.
x wedge dy. Great. So this is the beta we actually want to integrate over. That will give us the flux corresponding to the vector field you are given with. So now next point is to parameterize the surface. So the coordinate is already set up. So x, y, z coordinate, we can use two of those as parameters, right?
Yeah.
So